Okay, welcome back. So let's continue from where we left off. So another one more reduction I want to do is to show that you don't have to reduce from ATM to your target language, but in fact we'll use ETM here. So the language we want to talk about is EQTM. So the EQ stands for equality, and in fact I should say the E for ETM represents emptiness. But of course it's just the name of the language. So here we're going to be given two machines where, so M1, M2 are TMs, and in fact they have the same language. Okay, so so if M1, M2 actually is an EQTM, then in fact they have the same language. Even if they're completely different machines, they could still have the same language. Okay, so we'll show as a theorem that this is undecidable, as you might expect. It's actually a lot harder than ATM and ETM, but that's for another time. Alright, so we're going to show, via proof that ETM reduces to EQTM. So remember, ETM, actually we should make a supposed decider. So suppose, so I'm going to use Q this time, decides EQTM. Keeping these names straight is kind of annoying sometimes. Okay, so let's suppose Q decides EQTM. So now we want to build a decider for ETM. So remember, the decider or any decider for ETM must take a Turing machine, a single machine as input. But if I want to use Q here, if I feed M twice to this decider Q, then of course the language of Q is equal to the language of Q. So that will tell me nothing about whether M is empty. Sorry, the language of M equals the language of M, and so that tells me nothing about whether M's language is actually empty. So what we could do then is we can build a machine that is empty, that definitely has empty language, and compare it with M using this machine Q. So let's build a TM, I'm going to call it M sub empty, where the language of this thing is empty. It definitely is empty. So, of course, maybe just make the start state Q reject as an example. So it rejects everything. But now we're going to run Q, this supposed decider, on the two machines, M and M empty. Well, if M's language is empty, then Q will say yes, because it has the same language as M sub empty. So if Q accepts, then it must be the case that M's language is empty. So for our decider for ETM, we must also accept. So sometimes the reduction has you flip the answer, sometimes it has you have the same answer. It depends on the situation. But in the other case, if Q rejects, then reject. Because if Q says no, they're not the same, then M's language cannot possibly be empty. And so therefore we answered the question of whether it's empty. But as a final conclusion, since ETM is undecidable, EQTM must also be. Okay, great. So, of course, each one of these problems has its own a practical application. Like for EQTM, if you want to check whether a sample solution for a programming assignment matches a student submission, this shows you can't do that in the general case. So if you want to have a variant of EQTM that is decidable, you need to make some additional assumptions about it. But if you just have arbitrary Turing machines, you can't actually do this. Okay. So there's a one in the notes about this language, ALL TM. So it's like EQTM, but it's on the other end. It actually accepts everything. And in fact, this is undecidable too, as you might expect. And we can discuss on Piazza why this is undecidable. But you may think, well, okay, we are doing a lot of these reductions and they have a similar flavor, like especially these last two, where you take the input and then you make another machine that has these two different behaviors, and then you have that supposed decider differentiate between those two options, and then you can answer the question, say for example, whether M accepts W or not. Okay? So what we're going to establish is something called Rice's theorem. So to build up to that, we're going to say a property of TM languages, let's call it P. So this is a definition. So P is a property of Turing machine languages. If M1, M2 are TMs with the same language, they can be completely different machines, but if they have the same language, then either both descriptions are in P, so both machines have this property intuitively, or they both do not have the property. So I'll make that a little neater. Okay, so for example, all TM is a property of Turing machine languages because if you have two arbitrary machines, either both of them have language sigma star or both do not. It can't be the case that if they have the same language, one is sigma star and the other one is not sigma star. And so we need one more thing. If I gave you a property of Turing machine languages that says all the machines M such that M has a language, but that's decidable because every single Turing machine has a language, so every Turing machine is in there. So what we want is a non-trivial property. So a non-trivial property P. So in addition to being a property of Turing machine languages, a non-trivial property P also has that some Turing machine M1 has M1 being in P. So there is some machine that does in fact have the property, and there's another machine M2 has M2 not in P. So it can't be the case that P has every single Turing machine, and it can't be the case that P has no Turing machines in it. So what Rice's theorem says, it says that every non-trivial property is undecidable. And so how do we actually prove this? So we can't just start trying proofs like these ones where we just try a few and then say, yeah, it works in general, because there are infinitely many. And so we need to be careful about that. So let's work with an arbitrary non-trivial property. And we'll eventually show that P is an undecidable language. eventually. Okay, well, let's see. Well, we're going to make an assumption about P without loss of generality. So without loss of generality, we will assume that uh, M sub empty is a TM with the language of M empty being empty, and M sub empty actually is not in P. Okay? If it could be the case that M sub empty actually does have this property, whatever it is. But since we'll show it's undecidable, we showed in class that decidable languages are closed into complement. So in fact, I can substitute P for the complement of P if I wanted to get the assumption that M sub empty does not have the property. But we'll just make that assumption here. And we can assume this because it's a non-trivial property. There is some Turing machine that does not have the property. And let's assume that that's one of them. But we also had that there is a machine that does have the property. So let's let T be a TM with the language with the description of T having the property. So M sub empty is one machine that does not have the property, and T is some other machine, I don't know what language it is, that has the property. And so we'll use a reduction like the one from ATM to ETM that's almost exactly the same, but instead of being sigma star and empty here, it'll be the language of T and empty. And so that'll differentiate between the two behaviors that we want. We want to have M accept W if and only if the machine we're going to make has the property, has the language of T in this case. So we'll show that ATM reduces to P. So remember, ATM takes a machine and input as usual. And so, of course, we're going to construct ATM M prime. And here, not like that. So it's going to take an arbitrary input X. Okay, so here, as you might expect, we're going to run the original Turing machine on W. But if it rejects or runs forever, then what we want is that we want M prime's language to be empty. So as our thought bubble, if M does not accept W, we want L of M prime to be empty. And if M does accept W, what we want is the language of M prime to be the language of T, the thing that does have the property. Okay, well, if M does accept W, continue. So right off the bat, we're not going to change this first step. If M does not accept W, then M prime will not accept anything. So in fact, its language is empty. But here, M does accept W, so now we want M prime to behave exactly the same as T does. So run T on X, this arbitrary input here. So M prime now behaves exactly the same as T. So, and answer whatever T says. So it behaves exactly the same as T once M accepts W. And then now using our, suppose D decides this property P, whatever it is. So then we need to run D on M prime. If D accepts, well, let's just check. If D accepts, if it D says yes, that must mean that M prime does have the property. Well, remember, the two possibilities were it either was empty, which means it doesn't have the property, or it's T, which means it does have the property. But if it is T, that must have meant M accepted W. So for our decider for, the supposed decider for ATM, we need to say accept. And then, of course, the other direction, if D rejects, we're in the other case, and then therefore we reject. But ATM is undecidable, so P is undecidable. Which is pretty shocking. It's using almost the exact same idea as the ATM to ETM reduction, but now it's working in a general context. So in fact, we can show that, as an example, let's say all TM is undecidable. So I encourage you, if you can apply Rice's theorem, then absolutely use Rice's theorem. But sometimes you can't. As an example, if we have EQTM, this involves two machine descriptions instead of just a single machine description, which won't work. So it won't work here. But if we had the language, let's say M, it is single machine descriptions, but M has at least 7 states, and let's say L of M is empty, it might be undecidable, and I think it is here. But if I have two arbitrary machines that have the same language, they might be both empty or both not empty, but one of them could have at least 7 states and one of them has fewer than 7 states. So this is not a property of the Turing machine languages. So in this case, we can't apply Rice's theorem. But in all TM, it seems like we can. So let's see. Is it a property of Turing machine languages? So, i.e., if we have these machines M1, M2 with L of M1 equals L of M2, could it be the case that one of them is not sigma star and the other one is sigma star? But that seems ridiculous. Since they're the same language, the only deciding factor is whatever the language is. So they're either both in or both out. So we can write this as both are sigma star or both are not. So that's property. So now the other thing we need to show is that it's non-trivial. So we need to give an example of a Turing machine that is in all TM and another one that isn't. So an example would be, let's say, M1 with L of M1 being sigma star. So that definitely is in all TM. But another example that we need to show one is not in there, and an easy example is empty. So that definitely is not in all TM. And by these two, we can therefore say by Rice's theorem, all TM is undecidable. Okay, super. And of course we can show that ETM is undecidable in almost exactly the same way. We would just have to, in fact, the only thing we need to change for ETM is change that to be empty, and then change this to be not in, and then this one is in. But it's, and then of course all TM changes to ETM, but it's almost the exact same thing. So in fact, this is much easier than doing a reduction. You can always do a reduction, but you can't always apply Rice's theorem. So that's why I encourage people to use Rice's theorem whenever you can. Okay, so we're almost through the entire notes on Turing machines. So I'm not going to do all of them, but I'm going to do this half of the next part. And so you may be wondering, okay, well, some of these languages that are undecidable have this issue that we can't detect when they're running forever. If we can ensure that it doesn't run forever, or at least check that it will run forever in a finite amount of time, then we can actually solve some of these problems that are undecidable. So the way we do that is if we restrict how much tape we can use, then there's only so much that the machine can do before it starts repeating itself. So we're going to be talking briefly about something called linear bounded automata. So automata is just another word for these state machines, and linear bounded means that we're going to restrict the input. So we're going to restrict, not restrict the input, restrict the tape to be to what the input is. So it's exactly like a normal Turing machine, but now instead of having a one-way infinite tape, we're going to cap off the right-hand end. So we're going to put the input on the tape, but since we have two ends now, it'll be, and we can't shift the input right one position, we're going to be extra helpful and put end markers on the ends of the tape so we can actually detect when we're at the ends. But the computation and the behavior is exactly the same as a normal Turing machine otherwise. But if we, for example, if we get to the ends of the tape and we go off of the ends, then the computation stops, as you might expect. Okay, so of course we will call these LBAs. So what you may think is, well, what about A sub LBA, which is exactly the same thing as a Turing machine, but now M is an LBA, and M accepts W. Okay, well, let's see. If we saw that ATM was undecidable, but in fact, what we're going to show here is that this is decidable, which is actually pretty surprising. So by this immediately shows us that there are some languages that Turing machines can decide or recognize that LBAs cannot decide or recognize. Because if they were the same, then we can just run it on an LBA and it's decidable, and then we can show ATM is decidable, but that's not the case. So how do we actually show this? Well, I kind of alluded to it already, where if we are doing some computation and whatnot on the tape, and if we repeat a configuration, meaning that the tape head is pointed in the exact same place and that we're in the same state as before, and the tape contents everywhere else is exactly the same, then we will do the exact same thing over and over again because this machine is deterministic, like a normal Turing machine. So the idea is there are only so many possible configurations. So if we can compute the number of configurations, then if we run long enough to where we guarantee say by the pigeonhole principle, to repeat a configuration, then we just found out, hey, this machine actually is in an infinite loop. So compute the number of configs. So you can change the model slightly if you want, whether or not you can change these end markers. Let's assume that you can't change those two end markers. So what are all the possible tape contents? So let's say number tape contents. Well, let's see. We need to give some names. So let's say that there are Q states. There are, let's say, G tape symbols. And of course, there are N head positions. Maybe N plus 2, but it actually won't matter here. So let's say N tape head positions. Or maybe we can just set N to be N plus 2, the input size plus 2 to make it easier. Well, let's see. What are the tape contents? Well, these N positions can be any one of the tape symbols. So it's G possibilities for the first cell, G possibilities for the second, all the way through all N places. So in fact, there are G to the N of them. What about the number of states? But we already know that is Q. And the number of positions where the tape head could be, we already know that that is N. Well, the number of possibilities is just the product of these three, because it could be any of the tape contents, any state, and any position. So if we run the LBA for G to the N times Q times N plus 1 transitions, then we repeated a configuration. Repeated a config. Why is that? Because I have a lot of pigeons plus 1, and I only have so many pigeonholes. So by the pigeonhole principle, we must have repeated at least one configuration. So to decide A sub LBA, so we're given on input MW, where M is an LBA. So we'll compute G to the N times Q plus N plus 1, times N. And then we'll run M on W for at most G to the N Q times N plus 1 transitions. If M has not accepted W by now, it never will because it's in an infinite loop, so we reject, meaning that M does not accept W. But otherwise, it must be that M did accept, either accepted W already, or it has rejected W already, so output what M said, because it must have stopped by that point. Well, this is a finite number of transitions to apply. So doing this definitely can be done in a finite amount of time. So in fact, this is a decider, which is really interesting. So we can in fact decide A sub LBA because we can detect when we're in an infinite loop and when we're not in an infinite loop. So, and then that's not possible for an arbitrary Turing machine. Okay? So I'm going to leave E sub LBA for next time because it takes quite a bit of explaining to get through that. But we're almost done with the Turing machine stuff. So I'll see you all on Friday. And have a good Independence Day.